Let's talk about the SIR model for contagious diseases. Suppose there's a contagious disease spreading through a population. We're going to let S equal the proportion of the population which is susceptible, I be the proportion of the population which is infectious or infective. Some books say infective. We're going to let R equal the proportion of the population which is recovered. Some say removed, which includes those not surviving. A grim thought. Here's the way it progresses. People start out in S, susceptible. Some of them will move to infected, I, and then some of those will go to recovered. Well, eventually everybody ends up recovering or being removed because nobody's going to stay infected for the rest of their lives. People aren't infectious forever. We're assuming you can't get the disease again. In other words, you develop immunity, and the disease spreads quickly. So the only change in the groups, S, I, and R, is due to the disease. In other words, it's not like people are going to die from other causes. We're just looking at a short time frame. Here are the differential equations which describe how S, I, and R change. So ds dt equals negative alpha Si. First, it's negative because the susceptible group is only going to decrease. It never increases. People who are susceptible and get the disease, well, they end up moving from S to I. So it's got to be negative. Alpha is a contagion parameter. It reflects how contagious a disease is, how readily people go from S to I. And then it's going to be multiplied by the product Si. That's because the larger S is, the more susceptible people you have, the more likely people can get the disease. And also, the larger I is, the more infected people you have, the more you can infect people with the disease. di dt is going to be alpha Si because, again, those people who leave S are going to end up in I. That's why it's the opposite of this. It's alpha Si. Minus beta I. Here, beta is a recovery parameter. It reflects how quickly people recover. So this reflects people coming from S. This reflects people going to R, recovery. dr dt is just going to be beta I. So those are the people that recover or, frankly, are removed. R equals 1 minus S minus I. So people are either S or I or R. Since R is 1 minus S minus I, we can just focus on S and I. We're not going to pay attention to R. How do we choose the values of alpha and beta? Well, if a person is infectious for an average of 20 days, then you'd expect 5% of the infected to recover daily. So we would let beta equal 0.05. So basically, beta is going to be 1 over how long people are infectious. The basic reproduction number, R0, is the average number of infections produced when one infected person is introduced into a population of susceptible people, and R0 equals alpha over beta. So this enables us to calculate alpha if we know R0 and beta. And often these just come through collecting data. Okay, for example, for COVID-19, the infectious period starts 2 days before the onset of symptoms and ends 7 to 10 days after the onset of symptoms. Estimate beta. So a person would be infectious for between 9 and 12 days. 2 days before the onset, 7 to 10 days after the onset. So beta is going to be between 1/9 and 1/12. We're just going to say beta equals 1/10. So let's say R0 is 2.6. In other words, on average, the disease is passed on to 2.6 people in a susceptible population. Find alpha. Well, since R0 is alpha over beta, which is alpha over 0.1, which is 2.6, we have alpha equals 0.1 times 2.6, in other words, 0.26. Sketch the phase portrait for S and I. Assume that initially 1% of the population has COVID-19. So this is what we have. Those were our differential equations from before. We found that alpha equals 0.26 and beta equals 0.1. Again, I'm not making up these values. These are just estimates of what they are for COVID-19. Plug those into the above equations and we get these differential equations. If 1% of the population has COVID-19, that means the proportion of infected is 0.01, which means the proportion of susceptible is everybody else, namely 0.99. Okay, so when you go to some phase portrait or some system or some plotter that plots systems of differential equations, and you plot these with S equals 0.99, I equals 0.01, and those differential equations we saw a moment ago, namely these, this is what you end up with. So this, again, is the S-axis, the susceptible, and this is the I-axis. So you start out with almost everybody susceptible, and then over time, fewer people are susceptible. Notice, eventually you get quite a few people infected, but then eventually it dies down. What percentage of the population never gets infected? Well, we can see that from here, around 10%, because the disease dies out by the time you get 10% of the people who are susceptible. How would we change the model if 20% of the population were immune initially, whether it's, due to previous infection or vaccination or whatever? We'd use S equals 0.79, I equals 0.01, instead of S equals 0.99, I equals 0.01. Again, because you don't have 99% of the people susceptible, you have only 79% of the people susceptible. Herd immunity. Herd immunity occurs when enough people in a population become immune to a disease through vaccination or through previously getting the disease, so that the disease is less likely to spread to those who are not immune. So in this case, notice that eventually, once you have only 10% of the population that's susceptible, then the disease kind of dies out, because there are so few people that are susceptible that eventually you just don't have that many people who have the disease, and there are so few people who are susceptible that they're just there's unlikely to be encounters between susceptible and infected people. So the disease just dies out. Note that dIdt equals alpha Si minus beta I. We can factor out the I. This equals 0 if S equals beta over alpha. If S equals beta, if S is less than beta over alpha, there's no epidemic because I is decreasing. But if S is greater than beta over alpha, there is an epidemic because I is increasing. This value of S is called the threshold value. To the right of this, I increases. To the left of this, I decreases. Now, there are ways that we can refine the model. There can be different ages. Different ages affect the number of contacts. For instance, school children are very likely to be around lots of other people, whereas people who are elderly or living in a nursing home, they're not going to encounter as many people. So that affects the rate of transmission. You also can incorporate vaccination into your SIR model, and you also have the waning of immunity, because COVID-19 immunity doesn't last forever. You also have different variants which can crop up. That's another way to refine the model. And that's why with COVID-19, we're not seeing a situation like this. It's not like it's dying out. That's just not happening. Here are the basic reproduction numbers. R0 for diseases. This is a reflection of how infectious they are. At one end of the spectrum, you have measles, very, very infectious. Initially, COVID was not that infectious, but then the Delta strain, and especially the Omicron strain, were very infectious. And then, of course, the common cold, not as infectious. MERS, even less infectious than that.